In this video, we're going to cover the basic information about vectors that we need to understand in order to be able to study two-dimensional motion. In one-dimensional motion, we were able to handle the vector nature of our quantities like displacement and velocity and acceleration by just using plus and minus. So if the vector was to the right, it was plus. If it was to the left, it was negative. But we can't use that approach in two dimensions. Notice I have a couple vectors drawn here, vector A and vector B, and now we have all of the directions possible in two dimensions. So we no longer can do a simple plus or minus. Instead, what we do is we talk about two key values for a vector: the magnitude of the vector and the direction of the vector. The magnitude of a vector represents the length of the vector. In other words, how big is the quantity that the vector is representing. Key thing about the magnitude of a vector, it's always positive. And when we're representing the magnitude of a vector, we just write the vector without a vector sign over it. By the way, that arrow is the symbol that represents that is vector A. But if we're only talking about the magnitude of vector A, we would just write it with an A with no arrow over it. The other key quantity for a vector is the direction, and we specify the direction with respect to the positive x-axis. I would call that angle then theta A, and that would be the direction of vector A. So for example, in this case, it looks to be about 40 degrees. Notice that we always measure the direction of the vector with respect to the positive x-axis. If we look here at vector B, I can see that theta B looks to be about negative 40 degrees. Now usually in physics, when we're in the fourth quadrant, we use the negative angle as opposed to going all the way around and saying that the angle is 320 degrees. Obviously that's not wrong, but it's more convenient to use the negative angle, as we'll see when we get into doing physics problems. All right, let's look at vector C. What is the angle for vector C? Well, it's the angle with respect to the positive x-axis. So notice that theta C would be 180 degrees. Does it matter where the vector is drawn on the page? So for example, is this vector different from this vector? The answer is no, because you'll notice that it still has the same length and it has the same direction. So the length A is the same, the magnitude. The direction theta A is the same, 40 degrees. And so those are identical vectors. It doesn't matter where you draw the vector on the page. The only thing that matters is how long the vector is and what direction it's pointing. Let's look at how to add vectors. We're going to learn first how to do it by drawing pictures, and then later we'll learn how to do it with using components. The steps are pretty straightforward. If I want to add vector A and vector B, the first thing I do is draw vector A. Then I want to take the tail of the second vector, vector B, and place it at the head of vector A. So there's vector B, and then my resultant vector goes from the tail of A to the head of B. Vector C then is equal to vector A plus vector B. Let's look at subtracting vectors. It turns out that subtracting vectors is very similar to adding. In fact, all we have to understand is what do we mean by minus a vector. And it turns out that if vector A looks like this, then negative A is simply a vector with the same magnitude but in the opposite direction. Therefore, when we're thinking about what is B minus A, what we want to think about is it's the same as adding the negative of vector A to vector B. All right, let's look at an example. So I want to take vector b and subtract vector a. The first thing I have to do is figure out what is negative a. Well, if a is to the right, then negative a would be a vector pointing to the left with the same length. And now I'm just going to do my standard addition. So I draw the first vector. So there's vector b. Now I'm going to add vector negative a. So I put the tail of vector negative a to the head of vector b. And then my resultant vector goes from the tail of b to the head of a. So that's vector c, where vector c is equal to vector b minus vector a. Let's talk about multiplying a vector by a scalar. Remember, a scalar is just a number, no direction associated with it. When we multiply a vector by a scalar, all we're doing is changing the length of the vector. Let's go through a couple examples. So if I have vector a, and I now want to find out what is 2 times a, I just take a vector that's in the same direction as vector a, but is twice as long. Okay? So that would be vector b. If you're multiplying by a negative scalar, then not only will you change the magnitude of the vector, but you will flip the direction. So if vector d is negative 3 times vector a, we want a vector that's in the opposite direction of a and 3 times as long. Therefore, that would be vector d. Let's review the important information from right triangle trigonometry that you need to understand vectors. I'm sure at some point in your study of math, you memorized SOHCAHTOA. And that's really the key stuff that we have to remember when we're doing right triangle trigonometry. By the way, we're going to be using degrees in this part of the course, so you do want to make sure that your calculator is in degree mode. Let's remember what SOHCAHTOA stands for. If I label my triangle here with that angle as theta, that side A, that side B, and that side C, we know that the SO of SOHCAHTOA tells us that the sine of theta is equal to the opposite over the hypotenuse, so A over C. That the cosine of theta is equal to the adjacent side over the hypotenuse, or B over C, and that the tangent of theta is equal to the opposite over the adjacent, or side A over B. Okay, that's kind of the basic stuff in terms of just definitions of sine, cosine, and tangent. We want to understand more than that, though. First of all, if we're given the sides and we want to find the angle, then depending on which sides we're given, we would simply want to use one of the inverse sine functions. So in other words, theta would be equal to the inverse sine. And by the way, you may have learned that as being called arc sine. That's kind of the older notation. Inverse sine of A over C. Or theta could be written as the inverse cosine of B over C. Or theta could be written as the inverse tangent of A over B. One thing that we definitely want to be able to do is to draw what these functions look like. Let's draw sine and cosine. We know that sine functions look something like this. And there are a couple key characteristics you want to remember. First of all, we know that the maximum value of sine is 1 and the minimum value is negative 1. But then we also want to remember what is the repeat period for the sine. In other words, what is the sine periodic over? Well, if we're dealing with radians, we'd say that the sine repeats every 2 pi, or for us, if we're talking about degrees, it repeats every 360 degrees. So sine theta is periodic over 2 pi or 360 degrees. Cosine is the same, except that it starts at 1. And if we're looking, therefore, at a cosine graph, again, it goes from a maximum value of 1 to a minimum value of -1, and it repeats every 2 pi or 360 degrees. All right, why do we need to know this stuff about right triangle trigonometry when we're dealing with vectors? Well, the reason is that when we want to specify a vector, we can either do it by giving the components of the vector or by giving the magnitude and the direction. Remember, the magnitude of a vector is just the length of the vector, a, and the direction is just the angle with respect to the positive x-axis, and I'll call that theta a. You'll also notice, though, that this vector can be thought of as being made up of a vector in the x direction plus a vector in the y direction. Well, this we call ax. That's the x component of the vector. And this is ay, the y component. Notice, by the way, that we could draw ay over here as well, and we could draw ax here as well. Well, if we look at this and use our right triangle trigonometry, you'll notice that since we know that the sine of theta a is the opposite over the hypotenuse, well, that would be ay over a. And therefore, if we know the magnitude and the direction of a vector and we want to find the y component, we just take the magnitude and multiply by the sine of the angle. In the same way, since we know cosine of theta a is equal to ax over a, if we want the x component of the vector, we simply take the magnitude of the vector and multiply by the cosine of theta a. You definitely want to be very comfortable with using those formulas. Now, let's say that instead of finding the components from the magnitude and the direction, how about if we know the components and we want to find the magnitude and the direction? You'll notice the magnitude of the vector can just be found by using the Pythagorean theorem, that the magnitude is just ax squared plus ay squared under the square root. You can also see that I can get the angle from the components directly by using the inverse tangent. The inverse tangent of ay over ax is theta a. Again, very important to be comfortable with those two formulas. So notice we now have a way to go from components to magnitude and direction, or from magnitude and direction to components. And you're going to find that we do that a lot. In fact, in almost every two-dimensional problem, you'll be having to do this process. Let's look at an example. Again, we want to make sure that our calculators are in degree mode. So why don't you go ahead and see if you can do this on your own. Pause the video and then start and see how you did. The question is, what are the components of a vector with a magnitude of 23.5 and a direction of 142 degrees? We know that to find the x component of a vector, we just take the magnitude of the vector times the cosine of the angle. Well, we're told that theta a is 142 degrees. You want to make sure to plug in that angle. Don't plug this angle in, because if you always use the angle with respect to the positive x-axis, then not only will you find the components correctly, but you'll find whether they're positive or negative, and that's important. In this case, then I'm just going to plug in 23.5 for the magnitude times the cosine of 142. And as long as I've got my calculator in degree mode, what I get is negative 18.5. Notice, by the way, that the component came out negative, and that makes sense. I can see the x component of the vector is negative. To find the y component, I'll do a sine theta a. 23.5 times the sine of 142. If you work that out, you should get 14.5. Notice that we get a positive value, and that makes sense because I can see the y component of that vector is positive. Let's test out one of the other formulas we've talked about, and that is going from the components back to the angle. We said on the last slide that we can find the angle by taking the inverse tangent of AY over AX. Go ahead and try that calculation and see if you get back to 142 degrees. Okay, so I'm going to do it. I plug in AY, which is 14.5. divided by negative 18.5. And what I end up with is negative 38 degrees. Well, notice I didn't get back to what I thought I would get back to. I didn't get 142 degrees, I got negative 38 degrees. So let's dig into why that happened. I want to remind you of the graph of tangent. A few slides ago we reviewed what the graph of sine and cosine look like, but we didn't talk about tangent. Remember that the tangent goes from negative infinity to infinity over that range of negative 90 to 90 degrees. Well, you'll notice that if the tangent looks like this, then the inverse tangent looks like this. In other words, if you put in any number, the biggest angle you can ever get out of the inverse tangent is 90 degrees. And the smallest number that ever comes out of the inverse tangent is negative 90 degrees. That's why we couldn't get back to 142 degrees when we use the inverse tangent. The biggest number we could get would be 90 degrees. So how do we deal with this problem? Well, we just have to think about using the inverse tangent and look at what quadrant we're in. So let's go through the 4 quadrants. If we're in quadrant 1, we don't have any problems. If I want to figure out what theta is and I know AY and I know AX, I can go ahead and just use the formula and it works correctly. Now, if I'm in quadrant 4, it also works correctly. So if I put in AX, you'll notice that AX is still a positive component. AY is now negative. But if you plug that in, you will actually get this angle no problem, because we saw that inverse tangent can give an angle as small as negative 90 degrees. Well, that covers quadrant 4. Now, in quadrant 2, here's the problem. You'll notice that AY is positive and AX is now negative. The problem is that inverse tangent can't tell the difference between that situation and quadrant 4, because when you divide AY by AX, you're going to get a negative value, whether AY is positive and AX is negative, or AX is positive and AY is negative. And so what inverse tangent gives you for the answer is instead of giving you the answer that you want, which is this angle, the angle with respect to the positive x-axis, it gives you this angle. But you'll notice that all you have to do to get the correct angle once you've got this angle theta is add 180 degrees to the answer. So for example, let's say that I got a theta of negative 30 degrees. If I add 180 to that, that would give me this angle, which would therefore be 150 degrees. And that's the angle I want, the angle with respect to the positive x-axis. The same thing is going to be true in quadrant 3, because in quadrant 3, you'll notice that both AY is negative and AX is negative. So the problem is when you divide AY by AX up in the formula, we get a positive number. So inverse tangent can't tell the difference between quadrant 3 and quadrant 1. So the inverse tangent is going to give you this angle theta. But notice the angle we want is that entire angle. But once again, let's say theta came out to be 30 degrees. All we need to do is add 180 degrees to the answer. And so in this case, the correct answer would be 210 degrees. That would be the angle, again, from the positive x-axis. So just remember, the inverse tangent works fine in quadrant 1 and quadrant 4. If you're in quadrant 2 or quadrant 3, you have to add 180 degrees to the answer that you get. Go ahead and try this problem and then restart the video. So in this problem, we were supposed to find the magnitude and the direction. The magnitude we know we can just get from using the Pythagorean theorem. So we've got the square root of ax squared plus ay squared. And we got to be a little bit careful here. We've got negative 60.2 squared plus negative 90.3 squared. And when I worked that out, I got that the magnitude was 109. If I do the inverse tangent to find the angle, the inverse tangent of ay over ax, so that's the inverse tangent of negative 90.3 divided by negative 60.2. Notice that this is a situation where we're in the third quadrant. The angle that I got when I calculated that was 56.3. But what I have to remember is that what inverse tangent did was it found this angle. And what I want to do is I want this entire angle, and so I've got to just add 180 degrees. So my final answer would be 180 plus 56.3, or 236.3 degrees. By the way, notice in significant figures here that 180 is exact. And so I want to keep all the way to the last decimal that both numbers have in common, which would be that 0.3. Let's look at the concept of unit vectors. A unit vector is a vector that has a length of 1 and is directed along one of the axes. So we have 3 unit vectors. The unit vector that points in the x direction is unit vector I. In the y direction, we have unit vector j. And if we have a three-dimensional problem where we have x, y, and z, then in addition to unit vector I and unit vector j, we have unit vector k. You'll notice that the notation for unit vectors is different than other vectors. We write our vector with this little caret over the top, and it looks like a hat. So literally, when we say this, we call this I hat. So we have I hat in the x direction, j hat in the y direction, and k hat in the z direction. The reason that unit vectors are useful is they allow us to write a vector in terms of its components. In general then, vector A can be written as the x component times I hat plus the y component times j hat plus the z component times k hat. Let's look at a two-dimensional example. If we have a two-dimensional vector that has an x component of 15 and a y component of 12, then vector A can be written as 15i plus 12j. And notice it's just saying if you go 15 in the x direction and 12 in the y direction, you get to the right point. You get to the point of that vector. Let's look at adding and subtracting vectors with components. If we want to figure out what vector C is, we know already how to do that by drawing pictures. I draw vector A, I take the tail of vector B and put it at the head of vector A, and then vector C goes from the tail of A to the head of B. But obviously we want to do this more analytically. You'll notice that what we first have to do is resolve our vectors into their components. So in other words, AX is that. Here's AY. Here's BX. And here's BY. And pretty quickly we can see how to find CX and CY. In other words, CX is going to be this entire length, and CY is going to be this entire length. And therefore we can see that to find those components, we're just going to add the components of the two original vectors. So CX is just going to be the x components of A and B, and CY is just going to be adding the y components of vector A and vector B. Let's do an example problem to see how adding vectors works with components. Our problem says a man walks for 32 meters in a direction of 37 degrees with respect to the x-axis. He then walks for 11 meters in a direction of 95 degrees with respect to the x-axis. Where does he end up? First thing I want to do is I want to draw it out so I have a basic idea of what it looks like. So our man walks for 32 meters at an angle of 37 degrees. So that's 37 degrees. And then at this point, he walks at an angle of 95 degrees. So in other words, here's the x-axis. Here's straight up. So 95 degrees would be a little bit like that. And it's 11 meters. I can see that vector B then is about a third of the size of vector A. And what I want to find is vector C, where vector C looks like that. So where does he end up? What I want to find is both the length from the origin, which is the magnitude of vector C, as well as the direction. So I want to find theta C and C. As we just learned, the first step is to find the components of the original two vectors. Now, you might want to go ahead and try to do this problem on your own, and then restart the video and see if you got it right. Once again, I'm in degree mode. Let's go ahead and find the components of vector A and vector B. We know that AX is A cosine theta A. So that's going to be 32 cosine of 37 degrees. And I got 25.6 meters for that. AY is A sine theta A. So that's 32 times the sine of 37 degrees. I got 19.3 for that meters. BX is B cosine theta B, or 11 times the cosine of 95 degrees. Again, always using the angle with respect to the positive x-axis. I got negative 0.959 meters for that. That makes sense. It's both negative and small. BY is B sine theta B. And when you take 11 sine of 95 degrees to three significant figures, you're just going to get 11 meters. And again, that makes sense because this vector is almost completely vertical. Now, to find the components of our resultant vector, vector C, I'm just going to add AX and BX to find CX. And I got 24.6 meters for that. CY is AY plus BY. And I got 30.3 meters for that. And then using the Pythagorean theorem, so cx squared plus cy squared all under the square root, I'll give you the answer I got. I got 39 meters. And for theta c, using the inverse tangent of cy over cx, I got 50.9 degrees. One of the things that I always want to stress to you is when you get answers, think about them and see if they make sense. You'll notice that vector c is not that much longer than vector a in the picture. And so it makes sense that if vector a is 32, an answer for vector c of 39 seems very reasonable. Also, we know that theta c should be maybe not quite double theta a, but something maybe 1.5 times. And so again, a final angle of 50.9 looks like it makes sense from our picture.